Hi everyone. Hello. Yep. Okay. Welcome to Google's Developer Space channel, and thank you for tuning in to today's live stream session. Yeah. So for today's session, right, we are very excited to be hosting Data Science Singapore, and as you know, the team always bring us great content and great speakers. So before we begin, let me briefly introduce who we are and what we do. I'm Lawrence from the Google Developer Relations team. And Google Developer Space is a platform for developers and startups around the region to learn, connect, engage, and be inspired. Yeah. So without further ado, I will hand over the stage to Sonima to start today's session. Over to you.
Thanks so much, Lawrence. And just want to say that we're grateful for the continued partnership with Google Developer Space as we've moved to a virtual space because of the pandemic. It's really allowed us to diversify the speakers that we're able to get on the platform, and it's made, I think, a lot of what we do a bit more accessible to people who can't be here in person. Along that vein, I'm really pleased to introduce our speaker for tonight. Her name is Aqsa. She's the first female Google developer expert from Pakistan, and she's actually speaking to us from Pakistan today. She was a mentor 3 times at the Google's Women Developer Academy and is presently the tech lead for machine learning at Red Buffer Analytics, building AI and machine learning software services. Aqsa strongly believes in the power of ideas to shape a better world and actively contributes her knowledge in the way that she's going to be doing so today. DataScience SG, as you probably know, is the longest running data science meetup in Singapore, and we're very pleased to have her here today. So without further ado, I'll hand it over to her to get started on this session today.
Hi, thank you for the lovely introduction. And hello, everyone. I'll just share my screen and then we can get going. So I hope my screen is visible to all of you. So today's topic is around practical machine learning for product development. As I've already been introduced, I am a tech lead at machine learning for machine learning at Red Buffer. I am also a Google developer expert in machine learning, and I'm also a tech blogger on Medium. So today we'll basically be talking about building different AI products. So one of them is about contract analysis and then property detection and then generating highlights for a basketball match through artificial intelligence. So before we dive into that, a little bit about what's my story. So I am an electrical engineering graduate from NAST. I got interested, basically I did my final year project in rehabilitation robotics. So I was always interested in robotics, but this was like my first proper project in robotics. And that's when I got introduced more deeply with artificial intelligence. And then I basically jumped off the cliff. So when I started, what that means is that I shifted my field and I started to learn more about AI, more about machine learning. I was working at a startup and they wanted someone to research on the artificial intelligence systems that Facebook and Netflix were using and how they were basically throwing in recommendations to their users. So I did a deep dive into those systems and researched a lot on how they were doing it. And that basically increased my fascination for the field. And then I started to learn machine learning, take courses online. So I did a lot of self-learning in that matter. And I do like to say that I'm pretty much a lot Andrew and the NG build. Since then, after that, I also became Pakistan's first female Google developer expert in machine learning. And as part of that, I am a small piece in the big global Google developer expert network that we have around the world. I'm also the first female machine learning GDE in Southeast Asia frontier region. So that's Pakistan, Nepal, Bangladesh, Sri Lanka. And since then, I've had the honor to speak at many different events locally and internationally. And I've also been a mentor thrice at Google Women Developer Academy. And I'm also currently a member for Road to GD program by Google. So now coming to basically what the breakdown for today is in terms of what you're here to learn from me. So when we're working with machine learning, initially uh, our scope is pretty limited when we enter what a machine learning domain, right? We know that this is something, some black box that's magic and that helps us do a lot of amazing things. But as we dive in deeper, we see that there are lot more to just machine learning. So some of those things are being able to debug machine learning systems, understanding when you get basically a new project, a new problem to solve. How do you begin solving that problem? What pipeline that is you can something that you can follow. And at the same time, once you have a machine learning system built and it's part of a bigger system, what are some of the integration techniques that you can use to integrate it to a larger system architecture? So we'll be talking about all of those things through some amazing project examples. So the first one of them is contract analysis. So I'm going to give a little overview of what the system is about. So for this system, the project was based on analyzing contracts with the legal contracts. And the system would basically initially take in input as a PDF. So you would have a PDF, a contract, and you would pass it to the system. And what was required of the system was to basically segment the PDF into logical sections and basically get entities extracted from that contract document. So you want to know details about the names of the people, what the contract is essentially about, what time, what date, is there any talk on pricing, and you want to know all of those things, all of those major clauses. And at the same time, you also want to use all of this to basically build a question answering module where if I want to know an answer to a question for a particular contract, I should be able to write a question and then basically get the answer for it. So we started off with taking the input PDF and first breaking it down into logical segments. So because there are different kinds of clauses in the legal domain, there's a lot of different kinds of clauses. There's governing clause, there's preamble, there's signature block, and there are a lot of many others. So we wanted to identify each of the clauses as well. So like, for example, this is signature block, this is preamble, this is the governing law, this is, and basically once we have all of that information, we would also be able to use this information to identify where the names would be, where the time and date would be, where they would be closing a deal with respect to money, in which clauses, and we would basically be able to use this information for that part as well. At the same time, also for the question answering module, because we would know that which kinds of clauses basically have which kinds of information for the answers. So the goal was that we had 30 different categories that we wanted to classify the clauses against. So as you can see there's governing law, liability, intellectual property, arbitration, many other, payment, dispute resolution, non-compete, and these are all the different kinds of clauses. The initial data that we breakdown that we had looked something like this. So as you can see that for many of the classes, we only have a few hundred samples. But then there are some where we basically have like samples in thousands. So we have like about 32,000 plus samples for the governing law and 16,000 plus for liability. But as we move down towards notice and everything downwards, we see that there are only about like a few hundred samples. So initially, the project was done using fast text model. So the classification was done using a fast text model that was trained on some of these classes. And we were getting, the team was getting very, very low accuracy on the class classification because there was so much high class imbalance between the classes. And this is one problem that we see in a lot of machine learning projects, and especially in natural language processing, we see this a lot. When something like this comes up, and you have trained one a model, and you've tried how the accuracy is, you've tested it, and you see that it's not accurate enough, it's not good enough for you. So starting off from here, you think, okay, what can you do to improve the system? What's one thing that you can do, right? And then so how do you solve this, right? So one answer that comes to your mind is, okay, what if I use a better model? Is there a better model that I can use to fix this problem, to get better accuracy? And that's what we did as well. And we thought, okay, why not use, is there a better model that we can use that exists out there that can be beneficial for us for solving this problem? And that's where we thought, okay, let's try out BERT. Now, BERT initially has been trained on a massive data set, right? And then inside of BERT, there are other kinds of BERTs that we can use, which are domain specific. So we thought, okay, is there a domain specific BERT that we can use for our problem? And that's where legal BERT came in. So legal BERT is trained on thousands of legal contracts. So we were able to use this and transfer learning to basically get a domain-specific solution, a domain-specific model solution for us. So now this is domain-specific, but how do you really solve for the imbalanced classes? Because still we still have imbalanced classes. We still have some samples which are in thousands, and we have some samples which are in hundreds. Now you can try to gather more samples for the classes where you have less data, but you'll still not be able to bring it up to thousands, right? And at the same time, that will also be very time consuming, and there would be additional complexity in terms of time and effort in that. So if that's not an option that you can go for one reason or the other, and you cannot gather more data, then what's something that you can do to solve such a high imbalance class for natural language processing? So one thing that you think of is, okay, I can do some, maybe there are techniques like data augmentation that I can do, but this is natural language processing, right? And then you can think, okay, maybe I can do upsampling and downsampling, and I can do something like that to make the model better. But then if we downsample classes from thousands to hundreds, where we're basically affecting the model accuracy for the classes where we do have a good sample number, we do have a count number, right? And since this is a natural language processing, you can't just take a sentence or a clause and a type of clause, for example, signature block type of clauses or preamble types of clauses, and say, okay, I'm going to upsample this, because it's different from other machine learning problems, and you can't just upsample like that in natural language processing. So what's one thing that we can do here now, right? So we came up with a solution that was cost-effective BERT. So is there something that we can do? So we've looked into trying to gather more data, and we see that that's not something that's feasible right now for us. We've looked into, okay, is there a way that we can augment the data, upsample it, downsample it? And those are also things that we cannot do right now. We have had a better model, and we know that the better model, which is trained on legal BERT, will improve the accuracy. But what else we can do for the imbalanced classes? How do we solve for that? Is there anything in the model that can help us solve for that? So cost-effective BERT is basically that solution. What cost-effective BERT does is it uses cost weighting in its loss function. So it penalizes the model more when you get labeled wrong for a class that had less samples. So if you get, for example, a governing law clause wrong, it penalizes you slightly less as compared to if you get a notice clause wrong, because the notice clause has less samples. So in that way, the model basically tries to focuses extra effort on trying to get the classes with less samples with better accuracy, better prediction probability. So it tries to adjust its loss like that. So this is a very nice technique that can be used for classification in natural language processing, where you have high imbalance between classes. So cost-effective BERT and weighted loss basically helped us solve this problem, and we were able to improve accuracy from cases where we had about 50% precision to improving it to about 0.83%. So for a lot of classes, we had like a jump of about 50% improvement. And for the ones that we were already doing good on, for example, governing law, etc., we were able to maintain that good accuracy for those classes as well. So then we moved on to see, okay, we analyzed the results and we saw that there was massive improvement. But then we saw, okay, we were getting low accuracy on preamble class for the real world data. So it performs good on the training data, but when we, when it's tested out in the real world, it's not giving us so much of good results. So then we went into dive into see how the data looks like for the preamble class, right? And we started to see, okay, what data is it basically not? What kind of data is it not classifying well? So once we did a deep dive into that, we saw that the preamble class data is not up to mark with how the real world preamble data is. And we saw flaws in the data that we were training it on with respect to preamble. So we took just that chunk of preamble class and we replaced it with new preamble data that we collected from Law Insider. And we retrained the model and we saw improvement. So we saw about like 90% of recall and precisions, but above 80%. And there was some massive improvement from 30 to 55% in some classes. And the confusion between different classes was also reduced. So the takeaway from this is that when we are initially starting to debug models, there are some questions that we need to keep in mind. So is there a better model that can be used? Is the model that we are using, what are the ways that we can improve that model? And then the most important question is that can the data be improved for the current problem that we have? So moving on to the next set of problems, which is on property detection. So this was a very interesting project where we had to detect a property in the sense that we had to detect whether there's a house or not, whether it's an empty plot, or whether it's a house under construction. So here are some of the samples for the data samples that we took from the aerial imagery. So the data set comprised of aerial imagery that we acquired from using an API, and we initially had a resolution of 1280 to 1280, and we converted these into 256 pixels, and we used that data. But taking a step back, let's see how do we want to start with this, right? So we have a set of problems, and we just have this one statement of problem that we want to detect property for house, empty plot, and house under construction. This is all the problem statement that we initially had. So we thought, okay, we want to do this for our country, for Pakistan, and how do we start with this ML problem? So obviously, the first thing that you need is data, right? So you need to gather data, then you need to label that data, then you would train some model, you would test that model, and you would evaluate it, right? And this question mark, this is where the iterative process would be, right? Because the improvement could be in anything. It could be a model improvement that you do and then you retrain. It could be a data improvement that you do. It could be another system improvement that you do, which would basically, after which you would retrain the model, retest it, and you would go through this iterative process. So starting off with data gathering. Okay, so what kind of data do we need, right? And where do we gather the data from? So we could use the aerial imagery, right? And we could use the aerial imagery. We could detect houses through that. We could detect empty plots through that. But how do we get those images now? How do we gather that data? Because you can't do that manually because it would be like massive effort and time cost. So we came up to link ourselves to this Mapbox API that we could use to gather aerial images. Given you could give it a set of coordinates, set of area, and it would basically give you the aerial imagery for that area. So now that we have all of those images, so what do we do next? We want to label that data. So whether or not is labeling required, right? Because for example, you're doing a cat dog classifier, and in that sense, you would have cat images and dog images, and all you don't need to specifically label them through a tool. but you can separate them out into dog images and cat images, and that would help with the model training. That would be all the labeling that you need. But in this case, what kind of do you need labeling? And that's something that comes with the definition of the problem. What kind of data labeling is required? So this is pretty important. And once you have decided the kind of labeling that's required, are there tools available for it? And how much time would it take for you to label data through that tool? So in our case, first we need to define the problem, right, and how it would look like. So we would get an aerial image, we would input it to our model, and what we want as an output is that we want to detect houses, empty plots, and under construction buildings. But now the main question is, okay, do you want to identify each house separately, right? Or do you just want the models to say, okay, these are houses, and you're not concerned with respect to, okay, whether or not it separates those houses as separate instances or not. So this is where this slide comes in, where we want to understand the difference between classification, object detection, semantic segmentation, and instant segmentation, right? So in our case, do we just need the object detection? Do we just want to identify bounding boxes around the houses? Is that all we need? Or do we want semantic segmentation? So we wanted semantic segmentation because the houses in many cases are cluttered together, and we want them to be identified separately, each house identified, each empty plot identified separately, and we are concerned about their respective boundaries. And we're also concerned with, okay, we want to be able to say, okay, this is house number 1, this is house number 2, this is house number 3. So we are concerned with instant segmentation. And that's where this problem, defining the problem, was very important, because this was going to define how we label the data. So since we've defined that we needed instant segmentation, so we went on to use a Label Me tool, which you can use to basically label all instances separately. So once we have the data gathered, we have defined how we want to label that data, we know what problem statement we're trying to solve. So what comes next is, okay, you want to train the model. Now we know that we want to train an instant segmentation model. So what options do we have out there? What models do we have out there that can help us train instant segmentation? So in that case, you would shortlist your models, and okay, there's Detectron, there's GCNet, there's Marks RCNN, and these are some of the models that you can use for training instant segmentation. So you would shortlist models based on, you would do your research, and you would shortlist models based on speed, complexity, usage popularity, their training time, etc. And usage popularity would also help you see, okay, how much success people have seen using this model for their problems, right? And how much support out there is that for this model, and the issues that people may face for these models, using these models. So once that is done, you can and it's not necessary that you use your research to end up with just one model to start off with. You can train multiple models in the start and analyze results, and then use that initial analysis of results that you have to choose a model to invest further time in. And once you start to invest further time in that model, then you need to give it enough time to basically train it, evaluate it, improve it, and this would be an iterative process. Where you would be investing your time and making improvements to train that model better for the problem that you are trying to solve. So some of the challenges that we faced were that, for example, the zoom level is lower for Pakistan. So for example, for USA, you can get a very high zoom level, but for Pakistan, it's limited to 18, and that's the highest zoom level that you can get. So what we did was that we took images at the highest available zoom level, and then we split those images using sliding window, and we labeled the zoom in images, and we followed a similar process for testing as well then. So when a new sample comes in, so that's also an image that we split in, and then we send to a model. And this is important because those are the kind of images that we have trained on. And that's the kind of zoom level that we have trained on. So we want to keep the consistency when we are predicting as well. And then we saw low initial accuracy. So when we analyzed it, we saw that we separated images where the accuracy was low, and we saw in those images that the empty plots were being confused with roads and parks. So it was identifying roads and parks as empty plots as well. And places where the houses were cluttered in societies, that's where it wasn't detecting them too bad. So in order to solve this, what we did was that we started to label roads and parks as well. So the model was then trained on not just houses and empty plots and under construction houses. It was also trained on roads and parks, and that helped it learn features for roads and parks separately from how an empty plot should look like. And for the cluttered societies, what we did, we increased the data because there was more complexity in those kinds of images where the houses were very close together and their spacing was very less, and they were not aligned in rows like other societies, other housing societies. So we increased the data for those cluttered societies, and we labeled more of those images for the model to learn better for those situations. So this is one sample output for how the model was identifying the different houses in an area, as each as a different instance. So the takeaways for this are that for an initial set of problems that we get, it's what are there are some standard questions that we need to ask ourselves when we are gathering the data, when we are labeling the data, and data labeling is very important with respect to the end goal that we have, so that we don't have to repeat the entire process. Data improvements are very important. Model shortlisting, model improvements, data improvements. These three are basically model improvements and data improvements are basically an iterative process that goes throughout the ML cycle for as long as you're working on that project. The last one of these is basically AI generated highlights. So this was an interesting project where we were supposed to take a basketball match video and generate highlights through AI. So we came up with multiple approaches. It could be video and audio based, it could be action based, it could be commentary based. So we want to know when some event occurred in that basketball match and capture that clip, right, and separate out that clip and identify that clip. It could be scoreboard based because when the score changes, you know that some event occurred, right? Or it could be hybrid of two or more of the above. So we did an initial research of, what could video plus audio based solution would look like, where that the crowd would always cheer when there's an event that happens, whenever there's a basket, whenever there's a 3-pointer, the crowd would obviously always cheer, and you could use that, and you could use the video clips to basically combine them up and detect events. And then it could also be action based. So you basically take the input frames and you classify actions into, the player's trying to shoot, dunk, dive for the ball, or that there's cheering. So you could make it action based as well. And in this case, you would obviously have these important events in the basketball match that you would shortlist, and you would try to identify these in the images. So this is what the final system looked like, and I'm not going to dive into how we were solving this problem and how we were coming up with a solution for generating the highlights. But the focus is that we built an ML solution for this to identify the clips where the highlights would be. But the important thing is that it was going to integrate with a dashboard. So where the admin person would be able to upload a video, and they should be able to send their request, and the machine learning system should be able to process that video and list down all of the events, the clips where some event has occurred, and at the same time also rate the excitement level for those events. So for example, for this clip, the excitement level was 8.5 out of 10. For this, it was just 6. So this was going to integrate with the dashboard. And multiple people were going to work on this admin panel, on this dashboard, and upload multiple videos. There could be multiple requests at the same time. And we don't want the system to break either. So in this, the architecture was very important on how we are storing the videos, because the videos were in gigabytes. So some of them were like very large videos, about 5 GBs, and some would be like, the minimum would be about 2 GB videos, because this is like the whole basketball match. So in that case, it was very important that we keep the architecture such that we're able to cater all of these things. So we're able to cater for everybody that's working on the web dashboard, and we're able to cater for the storage and all of these things. So we came up with a so this is what roughly the architecture looked like. So we were storing the videos on S3 AWS S3 bucket, and we were only giving the URL to the machine learning system. And then we were storing the results, which is basically the clip timings for the important events in a database, and the dashboard would pick results from the database. So the ML system would sit somewhere here where it's taking the URL, and it has to do all of the rest of the things with the video, get the results out, and push the results in the database with the clip timings and the events for the clip timing. So this is how it looked like. What basically what we were storing in the database. The JSON objects looked something like this. So the energy level basically defined how much excitement there was in the crowd for that event. And the start and end were basically the video times that showed the event occurring time, and you would have the descriptions. So in this case, it's excitement, but in many of the cases, as we progressed with this project, we were also giving out descriptions for whether this was a three-pointer, whether this was a foul. So we were giving those things out in the description as well. So this is where we were going to sync with the people that were working on the web dashboard, because this is what they were going to use to display everything on the dashboard. So there are three main things that we had to keep in mind. What request strategy would there be? So the video would be uploaded, but how would the request be sent to the machine learning server? How are we storing the videos, and how are we deploying the code base? So the solution for this was that we used RabbitMQ, which is the queue service that we used. So we use this for sending requests to the machine learning server. For storage, we use the S3 buckets, and for code base, we basically Dockerized, and we deployed our code on AWS servers. So how this architecture basically worked with RabbitMQ and everything else, this is how it looked like. So whenever you would upload a video on the dashboard, it would add a request to the queue. And the machine learning server would basically be listening to that queue consistently, continuously, 24/7. And whenever there's a request in that queue, it would pick it up, it would read the URL in that request, and it would download the video from the S3 directly on the machine learning server, process the video. Obviously, once the video has been processed, it would be deleted from the server for space to avoid space issues. And then whatever results or analysis that we have, whatever output we get from our ML system, we would update that in the database. The web service would basically pick up the results from the database and display them on the dashboard. So this is one example of how machine learning servers or machine learning systems are worked on separately, but then they fit in into a bigger system, into a bigger architecture. And some of the takeaways for this are that when we are working with some of these bigger systems, some of the common questions that we need to keep in our mind are with respect to storage, with respect to request strategy, deployment on cloud, time optimization, and basically syncing up all of these things with the web team with respect to, okay, how would the input look like from them, and what kind of input, what input they are getting, what input the machine learning server should be getting, what kind of output do they need to display back on the dashboard on their systems, and what output the machine learning server can give them to sync up with the kind of output that they need. I guess that's about it on the three different kinds of machine learning problems that we face when we're working with machine learning projects. I would love to hear if there are any questions.
Hi, Aqsa. Thanks so much for that. Really, well, I definitely have a ton of questions from the for all three different sections that you spoke through, and I can see that a couple of them are coming in. And as they do, maybe we'll just get started with okay. The first one from Daniel, and it's just around what database is used for the sports event use case.
Okay, so there were two things that we were doing in this. So we were storing the videos, and then we were storing basically everything related to the matches. So the match IDs, the match events, the clips, the JSON responses that we were getting from the machine learning system. So all of that, the database that we were using was Postgres SQL. But basically where we stored the videos was AWS S3. But since we were but I think you can use different databases as well. In this case, we were going more towards, we wanted the table structures, and we wanted it to be an SQL database and not a NoSQL database. So we went with that approach. And in that case, obviously, you can use MySQL, you can use Postgres. So that's what the approach that we went with. And for videos, we stored them in S3.
Perfect. Yeah. Got a couple more coming in. On the third use case around generating AI highlights, so how long did it generally take to process a basketball match?
Okay, so this is an interesting question. Thanks for bringing this up, because initially it took a lot of time to process the basketball match, because if it's a 1 hour video, and you have to process it frame by frame, so it's obviously whatever machine learning model you use, whatever techniques you use, it is going to take a lot of time. So this was actually an interesting problem that we came with. So initially we were for videos that were very large, we were even going up to like 40-50 minutes, and for minimum we were going about like 25 minutes per video. And this was a challenge because we wanted to we wanted to speed this up, and because that's what the product was about. So whenever the match ends, you are able to automatically generate the highlights in a very short period of time. So how we solved this was that the one thing that we did was that we split up the video match into smaller chunks, and then we processed them in parallel. And the second thing that we did, and so we would combine the results up at the end of that parallelization. And the second thing that we did was that we introduced multi-processing wherever in the code, in different functionality in the code as well. So and then we also experimented and came with an optimal FPS, that is so an optimal frame number that we could pick up from the video. So we could obviously not skip every frame, right? We couldn't pick like every 10th frame or every 20th frame, because that would reduce the accuracy. And at the same time, we could also not pick every frame to process it, because that would increase the time. So we experimented and came up with an optimal number that would give us good accuracy as well. So it was multi-processing. It was deciding how many frames we want to pick up, and it was dividing the video into chunks. And when we did all of that, we were able to bring it down to about 7 to 10 minutes.
Okay, so actually, and there are a few follow-up questions in this particular one, but maybe I'll add in one of my own. You also mentioned that part of how you decide what the highlights are not just by what's happening in the video, but also by what's happening in the commentary. So how did that kind of link up if you were actually choosing frames from the video itself?
We were so the commentary was obviously also with respect to the frames, right? So for example, if you're picking the first chunk, that would also be with respect to, okay, you have the necessary information that you need to process that chunk, right? So you know the times for that video. You also know what commentary is, what part of commentary is corresponds to that video chunk, right? So you have that information. And then we were also adding buffer, right? Because for the event, it can never be pinpointed to a single clip, right? So you can't say, okay, at 1 minute 30th second, 3-pointer occurred. So you always have to say, okay, between 110 to 125, a 3-pointer occurred. So that buffer actually helped us because we compromised on adding extra 2 seconds at the front and at the end of those clips to basically make sure that we're not missing out any part of the event and to basically avoid any errors if they were in alignment.
Yeah, and also on multi-threading and just splitting it all up. In terms of the processing itself, then how? Well, the question here is was the processing result cached anywhere? I'm sure it was. Can you maybe talk us through that strategy as well?
So yes, so if a video came up multiple times, so each video was basically we had a unique ID for every video, so for every match, and in that case, obviously, the results for that. By the results, I mean that we had a JSON object which held information like the start and end of the clip and what was happening, what important event was happening in that clip. And the scoring of that clip. So we had this information, all of this in a JSON object, and we stored that in the database. So if the same video basically came up again for the same match ID, for the same unique ID, then in that case, we would already have the information in the database, and we could basically use that and display that on the dashboard.
Okay, perfect. I think we have time for one more question, which is perfect. Esther asked, yeah, actually, great question. Why RabbitMQ as opposed to something that's maybe more industry standard, like an event streamer like Kafka?
Okay, so unfortunately, I've not worked with Kafka, so I won't be able to compare the two, but I have heard about it, and I would love to actually explore this and get back to you on this. That would actually be really nice.
Yeah, that's perfect. And you did talk us through kind of the using RabbitMQ specifically for request strategies. I think because you were also talking about event streaming and listening. Yeah, Kafka could be cool. Maybe then I'll add one question of my own. So in your second example, you kind of talked through the iterative process of model building. I'm just curious, how did you manage the versioning of your models? Were you using something like MLflow, or was that kind of done interactively within the team, or did you use any other tools?
No, so for iterative, so for the versioning, we did not use specifically something like a tool or something, but we did keep a track of, okay, this was model version 1, and we were storing the models, right? So we were using GitLab for all of our code base, so we were storing the different models that we were training on. And for the initial models, however, the ones that were not giving good accuracies, we did not keep a track of those. So we started to keep a track right after we felt, okay, this is where we're hitting improvements and we're working our way through, and this is where we want to go start off and keep a track of the improvements that we make. And we were also keeping a track of all the changes that we're making in for every iterative process. So whether we were making changes in the data, so how many more images we have added, what more locations we have added, and we were keeping a track of, okay, if you're changing any parameters in the model, so if we're increasing the batch sizes, or if we're decreasing batch sizes, if we're changing anything in the model parameters, if we're changing the number of epochs, if we're training it longer. So we were keeping a track of all of those for each of the model iterations that we were doing. So that helped us basically compare, right? So if I've trained two, so I have a version 1 model, and then after that I've trained 2 models, right? And in one I have different number of epochs and different batch size, and so I would be able to basically compare the results and make a conscious decision of which model, which change is basically moving me to the right direction.
I've also just seen one maybe last question that's popped up, which is also around the third example you talked us through. But how would the processing strategy change if the basketball event was streamed instead of batched?
Oh, sorry, apologies for that. Okay, streamed instead of batched. So I think the processing, a lot of it would remain similar, there wouldn't be, obviously you wouldn't have since you're streaming them, and I would say that the streaming would be in the sense that you're not having them, you don't have the whole 1 hour video. In that case, you have you have clips now, right? And you want to process those clips now because you're streaming it now. So it wouldn't be, because since it's a match, it wouldn't be like a second by second streaming. You would still need some buffer size to process it over. So in that case, one of the decisions you would want to make is, okay, what buffer size do you want that to be, right? So you want after every 10 minutes or after every 5 minutes clip, you want to process it, and then you want to, add it up to your generated highlights. So the processing would change in that sense. So from the buffer size now, okay, this is also something, since it would be a smaller clip, do you need storage for it? And if you do, then how would that work? Because you want all of that process to be faster now, right? If the goal is that, you get the results as quickly as possible. So the first question would be, okay, does that matter? Is it only about, streaming it and then getting the collective result at the end, or do you want the results right there and then, right? So in that case, there would be some decisions that you would have to make with respect to the speed. So the initial training would remain similar. The model predictions that process would remain similar. That instead of having a larger chunk of video being processed, you have smaller chunks that are being processed, and you have the results for those, and you're displaying those. But I think the more decisions would be around, okay, how fast you can make this, right? Mm-hmm. And how optimized with respect to time this can be, and without having any cost on accuracy. So I think the processing would change in the architecture and not generally with respect to what ML system you're building.
Yeah, that makes complete sense. And I know we're slightly over time. I do see one more question in the chat, and maybe I'll just rephrase it a little bit. Gosh asked, what's the rough estimation? Okay, so maybe if I rephrase it, how long approximately did it take from start to finish to implement and get these results for each of the 3 experiments you talked us through today?
Oh, that's interesting. So I think a lot of this depends on multiple things, mm-hmm. And I can. For the one where we were working with the contract analysis, so that was a project that was previously already done, and we were required to make improvement on it because they weren't getting good accuracy. In that way, I was working with a very experienced NLP engineer, and I knew that he came with years of experience, so he sped things up really quickly. Mm-hmm. So we made a lot of, we were able to improve results within a month because he came with a lot of pre-knowledge about births and losses and weights. So like that counts, right? So that experience does count, where you've already worked on multiple NLP projects, and so you look at the problems and you're able to pinpoint much quicker that okay, this is how I can solve it. And similarly, maybe if from today onward someone else actually comes up is facing imbalanced data set issues, they would be able to train BERT or use a weighted cost, or basically explore that solution, because that's the knowledge now they have from the start. So that's where I think that helped to speed it up. But for the property detection, we were starting from scratch. It took us roughly from data gathering, analyzing everything, to improving the models, it took us roughly about 2 to 3 months to get into a very above 89% accuracy for that model. This also includes labeling all of the data, which was a tedious and task, because you have to label every instance, and you don't want to go wrong with that. So you don't want to haphazardly label it. So, and the last one, AI generated highlights, it was a bigger project because we also had the dashboard, and we had, so there was, in that case, a lot of things also get delayed because you have your dependency on the other team as well, right? So you won't be able to test something out if they don't have the dashboard up. So those things were there as well. Mm-hmm. And there was a lot of research that was done on that project. So that took about 6 months for us to get. So we started off with researching, and then there was this development phase where the dashboard was being developed. We were developing the ML server, and then there was this testing phase where we saw that we're not doing well with respect to time, and it's taking too much time to process the videos. And then there was this whole cycle of how do we optimize this, and then there was like a month and a half spent on just trying to optimize the system and to bring the time down to less than 10 minutes.
Mm-hmm, mm-hmm. And I think related to that, we had another question come in about just monitoring drift. How did you actually do that, and how often did you need to retrain your models?
So for different projects, there are different things that matter. There are different basically thresholds that you want to stay in, right? For example, if somebody says, okay, I want an 80% accuracy on this, and someone else basically for a different project, they're okay with like a 60% accuracy. So those are some things that matter for you to. So the identification of that drift is dependent on that as well, and also on the problem statement. So for example, for a basketball match, if there are like about 50 important events that happen in 1 hour, and you miss out about 5, then that's maybe that's okay, right? But if you're on a property detection project and you have an image where you were supposed to identify about 10 houses and you're missing 5, then that's not good, right? So it also depends on that specific problem, and this is a metric that you need to set beforehand, and as you go along, that what are the metrics that you want to keep in mind. And once you have analyzed that, and once you have those noted down, then you need some way to basically evaluate the model, right? And you need to have some metrics and some things in place which you're using to evaluate the model continuously. And that would basically define when you want to retrain your model. So sometimes it's with respect to, okay, you have too much new data now, and you should retrain the model. Or when there's the data is beginning to change from what you trained the model on, so that's when you need to train the model. Or when you see, okay, you were getting good initial accuracy, but now the accuracies are going down, so you need to go back and see what's going wrong. So if it's is it performing badly on the new data, and is retraining a solution that you have come up with, then obviously you think around that. So the simplest answer to this would be that you decide what metrics and what key points you want to evaluate the model against, and then you keep a measure around that, and that's what helps you define when to retrain your model once in production.
Yeah, absolutely. And maybe the thing that I'd add to that is that you want to make sure that those metrics are consistent as well across the experimentation process. You don't want to be changing what you're measuring your models against.
Yes. Something that would stay consistent, right? So you don't want to change the metrics every now and then as well.
Yeah, absolutely. I think that's all. Thank you so much for going over with us, and thank you for your time today, Aqsa. Really
Thank you so
much.
Thank you so much for the invitation. The honor is mine.
Brilliant. Well, have a great evening, everyone, and thanks for joining. And we'll see you at the next DataScience SG meetup.
Thank you so much, everyone. Have a good day.